Okay, so time to get started. Real quick before we get back into the math, reminder about the attendance quizzes. So make sure to note the number down here. Make sure to take the attendance quiz on Sakai while it's still up. Remember, it starts 5 minutes before class starts, and it is removed and no longer available 5 minutes after class ends. So you have the whole class period. You've also got 5 minutes before class starts if you want to get ahead of the game. You got 5 minutes after class ends if you don't want to interrupt, if you don't come in early enough. Anyway, so for today, there's the number. Don't forget to do it. And off we go now back into the math. So last time we were talking about this word bijective while we were discussing linear transformations. So remember, the idea of bijective is that you have a perfect pairing. So for every output, there's an input, and for every input, there's an output. A perfect pairing between the target and the domain. Okay, so we were drawing pictures that look kind of like this. And, a perfect pairing, for example, might look something like this. Okay. All right. Sometimes it's called a bijection. Okay, so what can you do with this? Why do we care about this? It turns out that a bijective linear transformation has a really nice feature. And that's this theorem here, corollary of the above. We'll see why in a moment. So that is, if you have a linear transformation that is bijective, then the domain's dimension and the target's dimension are the same. All right. Now, why is this true? This is actually an easy proof. Like I say, this is a corollary, so I'm going to refer back to something we talked about last time, and that is this theorem up here. We proved this. Well, we proved most of this theorem last time. I still owe you a little bit. We're not quite going to get to that little bit today, but we'll get to it. We'll get to it on Friday. But that says that if you have a linear transformation, then the kernel and the image, the sum of their dimensions is the same as the dimension of the domain. Okay, now why is that relevant to what we're doing here? Keep in mind down here we're looking at a bijective linear transformation. Let's just think about what does this theorem here turn into if you have a bijective linear transformation. Well, if it's bijective, your domain V, right, your target W, there is a single vector in W that is the zero vector. This is a bijective linear transformation. Now, that means that the set of vectors that goes to that single zero vector is just a single vector. And side note, it is also the zero vector. Right? So this is the only vector that goes to the zero vector. And therefore, the kernel consists of just the zero vector. It's just an immediate consequence of it being a bijection. So what's the dimension of a vector space consisting of only a single point? Well, it's not one-dimensional. One-dimensional would mean it's got a non-zero vector that's a basis for the whole thing. It's zero-dimensional. So this number here is just zero. So that's the first thing that we get out of this being a bijection. The next thing we get, also from it being a bijection, is that for every vector in the output, there is a preimage in the domain. And that works for the entire target. Right? So that means that the image is actually the entire target. For every output, there's exactly one corresponding input. Therefore, every vector in the target has a corresponding preimage. So that means that the image is the entirety of W. So these conclusions that I've just drawn here, the green argument, if you will, tells us that the dimension of the kernel is 0. The blue argument, if you will, tells us that the image is the target, namely W. And notice what therefore the equation turns into. I mean, it just leaps off the page at you here, but it just turns into 0 plus dimension of W equals dimension of V. In other words, dimension of W equals dimension of V, which is what we were trying to prove. Okay, so nice, like I say, corollary of that rank nullity theorem that we had above. Okay, there is a wonderful consequence of this corollary. This is going to be a callback to chapter 4. You'll recall that way back at the beginning of chapter 4, I put an asterisk on the discussion and I said, well, we'll come back and fill this in later. Here we are. Specifically, I asserted way back at the start of chapter 4 that the set of solutions to a homogeneous differential equation with all these other details, that the set of solutions was an n-dimensional vector space. Now, we did prove at the time that it was a vector space. Now, it's just a subspace argument. But I never proved that it was n-dimensional. We used this a lot. Right? I mean, we relied on this fact, I'd even say, in chapter 4. We relied on it so that we could make dimension arguments and say, well, look, the number of solutions that I'm looking for, well, because it's n-dimensional, I know that the n solutions that I've found, if independent, therefore they span. So these kind of dimension arguments relied on knowing that it was n-dimensional. Never proved it. And now we're going to prove it with the greatest of ease. Reminder, the book proved it at great inconvenience back in chapter 4. Look back in the book. See how the book proves this result. It's quite inconvenient. I'm going to do it effortlessly here, using this theorem that we just talked about. Okay, so here's how we're going to do it. First thing I want to point out, the set of solutions is a vector space, already known. Right? We proved that back in chapter 4, subspace argument. Now this is going to seem weird. The next thing I want to point out is that the set of initial values, not a thing we've really talked about before, but let's suppose we want to think about this. Here's what an initial value looks like. If I were to think about what all initial values forms, well, initial value is it's a list of numbers that are the initial value and various derivatives of the function in question. So being as it is a list of numbers, it's a vector in Rn, if you choose to view it as such. So, nice punchline. The set of initial values, also a vector space. In particular, the set of initial values is Rn. All right, now, weird though this may seem, I'm going to create a linear transformation by the following formula. I know this seems strange, but it's going to work out powerfully in just a second. Here's a linear transformation. This linear transformation is defined by the following formula. It goes from the vector space of solutions into the vector space of initial values. And the formula for this linear transformation is, well, if you give me a solution, the value of this T transformation is just, well, what's the corresponding initial value? It's an easy formula. This T just says, oh, you're going to give me a solution? Okay, well, take some derivatives, plug in 0. Bam. That's how you evaluate this T function. Exercise for y'all is to confirm that this is a linear transformation. This is not that different from some examples that I've already suggested for y'all back in earlier in this section. Just show that this process of writing this down, is a linear. All right, who cares? Where does this go? Well, here's the thing. This function, this linear transformation, is not just a linear transformation. It is one-to-one and onto. It's a bijection. So this is a bijection between this domain and this target. And I'm going to persuade you of this, I hope, with an easy argument using the existence and uniqueness theorem. Again, way back to the beginning of Chapter 4, the very first thing that we said in Chapter 4. So, how do I know that T is 1-to-1? How do I know that I might not have sort of, two different solutions that yet still always give the same initial values? Right? How come that couldn't happen? Why can't we have two different solutions? Why can't we have two different inputs with the same output? Well, because the existence and uniqueness theorem tells us that for any set of initial conditions, there is exactly one solution. Therefore, these two functions here, these two inputs to T that have the same output, these two inputs have to actually be the same. And therefore, this function is 1-to-1. This T function is 1-to-1. Okay. Analogously, kind of, sort of. How do I know that this function is onto? How do I know that for every output of T, for every set of initial conditions, how do I know that there actually is a corresponding input? Again, that's what it would mean for T to be onto. I need to know that for every output, there's a corresponding input. I need to know, therefore, that for every set of initial conditions, I need to know that there is a solution with those initial conditions. And the existence portion of the existence and uniqueness theorem tells us that. The existence portion says that for any initial value problem, there is a solution. And then, of course, that is the Y for which T is equal to the given initial values. So, the existence and uniqueness theorem tells us that this function is not just a linear transformation. It's a linear transformation that is 1-to-1 and onto, and therefore the domain and the target have the same dimension. The domain, that's the dimension I'm trying to compute. I'm hoping, with fingers crossed, that is n-dimensional. And, well, I just proved that's equal to the dimension of the target. But the target is just Rn. And we've long known that Rn is n-dimensional. Right? And so there's the proof. Entirely done. The set of solutions to a differential equation of the given sort is n-dimensional. Right. Now, there's several things that have to be checked along in here, and I'll recognize that, right? I mean, you got to check that it's a linear transformation, and you've got to think through the fact that it's 1-to-1 and onto. But everything else in this argument is pretty sort of observational, right? Set it up in a certain way, look at it just from the right angle, and it's immediate that the set of solutions is n-dimensional. So now I want you all to compare and contrast. Go back into the book and look at where the book proves that the set of solutions is n-dimensional. They do it in Chapter 4, in Section 4.1, sort of near the beginning. And it's a pain. It's quite tedious. A lot of details, a lot of machinery, a lot of nitty-gritty, right? This is relatively, one stroke from a hammer in just the right spot. And it all falls together. Okay. All right. This proof that I just showed you is not in the book. So, this is the only place you'll find it. Okay, moving along. So we're going to go into Section 5.2 now. There's a certain amount of machinery in Section 5.2 we've got to set up. I'm going to make a bunch of definitions, a couple of observations, and we're going to define, as is given away by the title here, we're going to create an algebra of linear transformations, which sounds weird, right? What kind of things have we done algebra with in the past? Numbers. Right? You have numbers, you can talk about adding them and multiplying them and plugging them into polynomials and, what you think of as algebra. Right? Now, we also have an algebra of matrices. You can add them. You can multiply them by scalars. You can multiply them right? Some cases, anyway. Dimensions fit. We're going to do something kind of along those lines. Weird though it may seem, we don't think of linear transformations as elements on which you can do algebra, but we're gonna. Okay, so now, like I say, we got to set up some things. I've got to tell you what does it mean to add two linear transformations. If I want to claim that they add, well, I have to tell you how to do that. Likewise, I have to tell you how to multiply a linear transformation by a scalar. Good news, we've already done that, right? Linear transformations, after all, are just functions. And we have previously defined that what it means to add two functions is to get a resulting function that's evaluated by simply adding the output values of the original two functions. So another way to say that is that given this, that sort of allows us to conclude that. Right? The fact that we have an addition on output vectors gives us an addition on functions. Okay, so all of this, of course, takes place inside of the target. So another way to say this is the fact that we have an addition in W gives us an addition on the functions. Okay. Likewise, the fact that we have scalar vector multiplication in W gives us a scalar vector multiplication, well, a scalar linear transformation structure on linear transformations. Okay. All right. Here's what we can't do with this idea. Inside of W, don't forget, W is a vector space. In a vector space, you can add vectors. You can multiply vectors by scalars, but what we can't do is multiply vectors. That's not a thing in vector spaces, right? You can't talk about vector times vector. So if I would like to be able to multiply a linear transformation times another linear transformation, I'm going to have to kind of abandon this idea of, well, just, come on, rip it off out of W. That's not going to work. So here's what we're going to do instead. This is seemingly arbitrary, but I'm going to define a product of two linear transformations as coming from the composition. Very arbitrary. Pulling this out of a hat, this should not seem natural. It's totally arbitrary. Reminder, composition means whatever comes out of the linear transformation on the right is then plugged in to the linear transformation on the left. Okay. Now I can take this composition and I can say, let's call that an operation, but why would I call that a multiplication? It doesn't look like multiplication. Why don't I call it division? Why don't I call it subtraction? Why multiplication? Hard to see from here. The very simple reason for it is that here's what the algebra ends up looking like. If you define it to be a multiplication, then you get an algebra where it behaves just like a multiplication. So note down here, for example, it distributes across our existing addition, just like a multiplication kind of should. Likewise, it distributes the other way. Right? There's sort of a scalar associativity, just like there is with multiplication. There is a regular associativity. It really behaves a lot like multiplication does. So, arbitrary though it is, it's actually not unreasonable to choose to call this a multiplication. Okay. Alrighty. So, at this point, we've got a pretty persuasive algebra, right? This is the kind of stuff that you do with real numbers. This is the kind of stuff that you do with matrices. I don't know if y'all have seen any other kinds of algebras of things, but there's a bunch of algebraic properties. We do this kind of stuff in algebra all the time. So, kind of have an algebra. So these are our tools in the algebra of linear transformations. I will call your attention to one conspicuously absent rule, and that is multiplication is not commutative. And that's a disappointment, right? Commutativity is pretty handy when you're talking about algebra of numbers. A times B is B times A. Well, of course it is. I mean, 3 times 5 is 5 times 3. Obviously, right? Well, sadly, you kind of got to let go of that. When you're doing algebra of linear transformations, you cannot just, it just kind of switch the order of a multiplication whenever you want. It's just not true. And it's not hard to find counterexamples. You can just, honestly, if you pick up a couple of random linear transformations and do this, these are probably not going to be equal. Okay. Side note. This isn't our first time to have this disappointment. Matrix multiplication, also not commutative. Right? A times B is not equal to B times A in matrices. Right, so I'll call this a familiar disappointment. Yeah. Okay. All right. So what are we going to do with this? Okay, I should show you how to prove some of these. This is a pretty quick argument. There are, in fact, 9 assertions that I'm making here. We really ought to prove assertions when we make assertions. How am I going to prove these? There's 9 separate proofs. They're all kind of analogous. I'll show you how to prove this one. This is kind of what you might call right distributivity, right? So this T kind of distributes onto the right inside of that addition. So right distributivity. The way you prove it is you take the left side of the equation, you compute it. You take the right side of the equation, you compute it, and you just observe that you get the same thing both ways. It's a very straightforward calculation. Let me walk you through a couple of those steps. How would I compute this thing? Notice, first of all, that I have a product of that linear transformation and this linear transformation. And a product is defined by a composition. Notice that's all that I'm doing here. I'm first plugging in to the linear transformation on the right, and then whatever comes out of that, I'm plugging into the linear transformation on the left. Straight out of the definition, right? A product is a composition. Okay, right, fine. So how do I compute this thing? Well, here I have a sum, right? I've got a linear transformation R. I've got a linear transformation S, and by definition of addition, this sum, R plus S, I get by first plugging into R, then plugging into S. Notice I'm plugging the same thing into both R and S, and then I add the results. That's how I evaluate the addition of the transformations. So again, straight out of the definition, right? All you got to do in this process is just, each sort of step along the way, just carefully, delicately apply the definitions of the operations in question. I'm going to leave the second half here for y'all to think through on your own. It's again totally analogous, and when you do it, you get the same thing both ways. And therefore, these two functions are equal, which is what I wanted to prove for property 8. Okay. All right, everybody okay? Questions? Feel free. Yeah?
If you interpret the linear transformation as a function, and you use the fact that functions have those the first two properties that we mentioned at the beginning of the lecture to using a theorem that we had way earlier in the class,
okay,
with those 8 operations that you derived of linear,
You're talking about the 8 properties of vector space?
Yeah. If you can you use that fact to come up with these?
Not really. No, it's different things. So one thing you got to keep in mind, there's a lot of stuff that happens in linear algebra that kind of looks like other stuff that happens in linear algebra. In some sense, everything that happens in linear algebra is some version of nice things happen with linear combinations, in some sense, right? But what nice things and, in what context is a little bit different for every sort of thing. So what you're asking about is, operations that, define a vector space. We're defining they're a kind of a static sort of thing. A vector space just sits there. Here, we're talking about functions applying to vector spaces. We're not talking about just static vector spaces. So yeah, I mean, I totally hear where you're coming from. There is this kind of like, there's linear combinations. Everything works out with linear combinations in some sense, right? But the context is different, and you got to think it through appropriately in context. Very good question, and I appreciate that. But sadly, everything's different. Yeah. Okay. Right. Okay, so here's what we're going to do now. By the way, question comes up, reasonable question. Why are we thinking about an algebra of linear transformations? What are we going to do with this? And there's 3 big results that I want to get to. And all of them are callbacks to Chapter 4. So there's several things that I never did in Chapter 4. I never gave you any sort of initial motivation for, the very first thing we did in Chapter 4 was looking at a differential equation. Hey, let's try exponentials. Right, y'all remember that? I just said, pulling a rabbit out of a hat. Hey, I don't know, let's try exponentials. Maybe those work, right? And then magically it worked out great. Where did I get that from? That's a little bit of a scam, right? Is there any motivation for why we were trying exponentials, or am I just going to keep that from y'all? So today I'm going to show you what the motivation is. Like why? Not only why we know exponentials work. That's a plug and chug. You can just directly confirm. But what I'm going to show y'all today is why should they work? Why should I have tried that? Why should I have thought of those? Second thing I never really did back in Chapter 4. You remember that business with the repeated roots? If you have repeated roots, then you take the exponential, but then you also start multiplying by x. Never proved that. Right, we've used it a lot. We found lots of solutions. We connected it to real world problems. That's where resonance, that's why bridges fall down and stuff, right? So we made a lot of use out of that. This minor point never actually proved that, right? So we're going to prove that today. It's actually a pretty straightforward proof using this algebra of linear transformations. Lastly, that business in section 4.3 about the magic number, right? And the unfortunate coincidence. And in the case of the unfortunate coincidence, why do you multiply by x to the m? And I gave y'all this really sad argument about how at least it avoids obvious nonsense. Right? But that was not persuasive, wasn't intended to be persuasive, it was intended to be a sanity check, right? A plausibility argument. But I'm going to actually show y'all now why, I'm going to skip some ugly details, but morally speaking, why is it that multiplying by x to the m avoids the problems caused by the unfortunate coincidence? Okay, so all those are going to come up here in the next few minutes. So here's some groundwork that we've got to lay in order to do that. Just a couple of real quickies. Don't forget we've defined this linear transformation previously. D, right? D is the act of differentiation. D is a linear transformation. As one of the first ones that we did in section 5.1. Here's another one. We did not do this back in 5.1, but it's an easy proof. The act of multiplication by some C infinity function G. The act of multiplication by G is a linear transformation on C infinity. Now again, this is something you can prove. Reminder, I'm not saying that GF is linear. Certainly not. I'm saying that the act of multiplication by G is linear. It's linear on these input vectors, these input functions, F. Okay, so that's a linear transformation too. Now, quick observation. Using these, I can rewrite a Chapter 4 style differential equation. I can rewrite it by breaking down the left-hand side. Previously we referred to the left-hand side as, L. all of this great big mess here, L. Right? I mean, that's really sweeping it under the rug, right? I'm just taking this great big ugliness and putting it in a box and labeling it L. And then really learning. We know it's linear, and that's nice and everything. But the observation I want to make here is a much stronger observation, and that is that you can not only is this linear, but this is something that comes out of D and T. So specifically, this linear transformation L is made up out of D's and T's exactly like this. And this is something you can confirm for yourself immediately. Let's look at this term here, for example. What does this term do to y? Let's follow the rules. What does d to the n do to y? Well, it says take n derivatives of y. Okay, so that gives us the nth derivative of y. Fine. What does this t thing? This just says, okay, well, whatever you got from here, namely the nth derivative of y, multiply it by qn. And notice, you get exactly that. And likewise for all the other terms. So this is a pretty neat observation. Previously, again, I kind of just labeled the left-hand side operator as L. Now I am breaking it down into simpler things. That L is not just a thing. It is made up out of more elemental things. L can be thought of as sitting inside of the algebra that we just created of linear transformations. And a broad point that I think is really useful in lots of different ways. Algebra is nice. Algebra is a powerful tool. Algebra is powerful because we have algebraic properties that allow us to rewrite things in different forms from which you can draw different conclusions. Right? That's why high school algebra works in some senses, because we have rules of algebra that allow you to do things. And well, we have rules now of the algebra here, and I'm going to be able to rewrite L from this form into different forms, and that's where we're going to get big conclusions from. Okay, a notational observation. This is just notation. I'm going to rewrite that as this. I think this is a reasonable thing. Let me just point out what's going on. If I were to write, t, q, n, d to the n, and if I were to apply that to a function y, as just discussed, we get qn of x times the nth derivative of y. Now, what should this mean? What should it mean if I were to write down qn d to the n of y? And before I write down what I think, let me complain that as written here, it's not really clear what that is. I have not previously defined for y'all. What should it mean to multiply a linear transformation times a function of x? I haven't defined that. Yeah, but I mean, look what would happen if I just kind of do what seems reasonable. I guess I should take the nth derivative and then multiply by qn, and notice it gives me the exact same thing. So it just seems like a reasonable shorthand. We're going to use that as a shorthand for that going forward. The only reason I didn't write it like this in the first place is because I think it's nice to visually see that this is, in fact, the action of a linear transformation. I think in this original notation is more visibly the action of a linear transformation. And since we've got that established, now let's make our lives more convenient. Okay. All right. Okay. All right. We've already observed long ago that solving a homogeneous equation is looking for a kernel. So that's just a quick reminder. Now this next one is weird. This is weird for two reasons. I claim that our Chapter 4 linear differential operator L is the same as the characteristic polynomial applied to the D linear transformation. And you should be thinking two things right now, I propose. One of them is, Hey, wait a minute, can you do that? Isn't that a bunch of garbage? You can't just stick anything you want into a polynomial, right? Come on, polynomials. What do you put into polynomials? Numbers, right? You can't put a bicycle into a polynomial. What is bicycle squared, right? It's not a thing. You just can't, it doesn't make any sense. And likewise, can you do, is this not equally nonsensical? D is not a number. Can you actually plug something that's not a number into a polynomial? Well, generically no, right? But if you really break it down, what do you actually need to plug something into a polynomial? Let's just think it through. Whatever you put into a polynomial, you need to be able to raise to a power. In other words, you need to be able to multiply it by itself some number of times. I can do that with d. I know how to multiply d times d. So I can raise d to a power, not a problem. I will then subsequently, in evaluating the polynomial, I'll need to take some power of d. I'll need to multiply by numbers. Cool. I can do that. Oh, wait a second. There's several different terms in the polynomial. I'm going to need to be able to add those things. No problem. We have an addition on linear transformations, too. So, as it turns out, odd though it may seem, we have a perfectly good means of doing everything to d that we need to be able to do to evaluate a polynomial. So, it seems strange, right? But it's actually, strange though it appears, just fine to plug in d into a polynomial. Now the next thing you should be worried about is, okay, fine, so this isn't utter and complete garbage, but how in the world do I know that that gives me L? Yes, you had a question.
Could you show what GD would look like?
Yeah, I'm going to write that down in just a second. Yeah, absolutely. All right. So, is this equal to L? And sure. Here's how I know that it works out just fine. And by the way, we're talking about constant coefficients here. Of course, you have to talk about constant coefficients to be looking at the characteristic polynomial. So a constant coefficient L. Here, let me put a question mark on that. Constant coefficient L is something like this: a(n) d to the n plus etc. A bunch of terms that look like this: a1d plus a0. That's what L looks like from the previous page. And now, what is P? Well, P of lambda, don't forget, is copied from L. It is a(n) lambda to the n plus etc. plus a1 lambda plus a0, and therefore P of d is what you get when you take d and stick it in for all these lambdas. Therefore P of d is is a(n) d to the n plus etc. plus a1d plus a0. And so, yep, weirdly enough, totally works. How about that? Okay. All right. Okay. Moving along. Now, we've already bemoaned the fact that linear differential operators don't commute, right? We've got this algebra of linear transformations, and when you multiply, t times s is not always the same as s times t, so you can't just switch the order of the multiplication, and that's a huge disappointment. Here's an example of the failure in action, right? If you take derivatives after you multiply by g, then you're taking a derivative that gives you a product rule, and that gives you two terms. On the other hand, if you do the derivative before you multiply by g, well, then you only get that one term. So in some sense, this term right here is the problem, right? This is why, in this case anyway, it doesn't commute. Well, now I make the innocent observation that, if I had constant coefficients, if g were constant, that derivative would be 0, And that term that is a problem isn't there at all. And now these are equal. And therefore, in this special case where I have constant coefficient linear differential operators, these two things are equal. They do commute. Right? So that's really nice. So not only at this point do we have an algebra of linear transformations, but we have an even better algebra. We have a commutative algebra of linear transformations. So, okay, I know it's a lot of groundwork that we have to lay down, right? But this is all kind of got to get set. Okay, so I claim, I'll show you an example in a minute, that because of the commutativity, constant coefficient linear differential operators factor. They factor just like the corresponding characteristic polynomial would. For example, what if I have d squared minus 3d plus 2? Can I factor this? Are you allowed to just factor things? Well, yeah, no problem. I propose that this is d minus 1 times d minus 2. Now, can you do that? Is that legal? Well, the thing is, this would clearly give me d squared minus 1d, and then minus d2. Gotta be careful, right? The d is on the left, the 2 is on the right. Thus, I get d2, not 2d, initially. And then, let's see here, plus 2. But, because it commutes, that, because of the commutativity, is minus 3d. So you can see right here, commutativity is what you need to be able to make factoring work the way that you would sort of hope and expect that it would. So conveniently we have commutativity, and therefore everything in sight factors. And as a result of that, your characteristic polynomial, right? We didn't bat an eyelash when we factored the characteristic polynomial. That's old news. Yawn. But now, what that means is I can factor my linear differential operator the same way. And again, just keep in mind that the lambda just becomes a d. Everything else is the same. Okay, so this is the big win. I can rewrite linear differential operators in a factored form. And now let me just start showing you how powerful this result is. Let's go back to the very beginning of chapter 4, section 4.2. How do I solve this differential equation? And you remember, this is where I pulled the rabbit out of a hat and I said, hey, I got an idea. Let's try exponentials. And of course it worked, right? Okay, but where did that come from? What was my instinct to try exponentials other than I asked somebody showed me? Right? Well, here's I think a pretty good point of view on that. Let's rewrite L. Right? L is, in fact, this factored product of linear transformations. Don't forget everything commutes, right? So I can take this great big product. I can take a single factor from inside of there, pull it out over to the right. Everything else, whatever is left, all the rest of this, I don't know what it is. It's a bunch of factors. Let me just call it Q. Whatever. Who cares? Right? So this initial differential equation that I had, rewriting it in a factored form, shuffling around like this, I now have a separate differential equation to try to solve. And I can make a clever observation. If my goal is to make this monster equal to 0, if I could just make this part of it equal to 0, that's clearly a win. Right now, there's other ways, probably. There's going to be a lot of different solutions, lots of y's that would make. But if I made this thing 0, that's going to work. And that is a first order differential equation. In fact, it's a natural growth equation, and we already know how to solve those. Right? So that's the motivation. This is why one would think correction. This is why one could have thought to try exponentials. Simply factoring the linear differential operator gives rise to a much simpler differential equation that you can then easily speculate about. So I think that's a cool move. Again, this is not in the book, but it's a good trick. Next question. What's the deal with the multiplicities and the extra factors of x? This is a real easy argument to make. We'll call this the last thing for today. First, a quick observation. We know we're going to be dealing with a bunch of linear transformations that look like this, d minus r. I would like to, for my own convenience, see what does a factor like that do to a function like this. And of course, now, why am I interested in functions like this? Well, because these are what I'm claiming are solutions. Right? I'm sort of asserting that all these are going to be solutions to the differential equation that involves factors that look like this. So let's work out this one time so I don't have to do it a million times. And what you notice is D product rule gives you that. That's just the product rule. Minus R gives you that. That's just multiplying. Notice that these two terms cancel. Lovely. And therefore we end up with just this term as our answer. So I'll say it this way, a nice punchline is that what d minus r does is it simply removes 1 from the exponent. That's the headline. D minus r does to a function like this primarily to remove 1 from the exponent of the monomial factor. Yeah. There's a factor of k out. It's going to turn out that this scalar factor out here doesn't matter, but anyway, it's there. Quick side note, of course, that number has to be the same as that number. Okay. On the other hand, immediate calculation d minus r on the exponential gives you just 0. Okay. So, here's our situation. I'm looking at this linear differential operator. That's my L. The solutions that I would like to prove actually work, my proposed solutions are these, right? So just remember, flashback to chapter 4, the assertion was that if you have a root of multiplicity m, then you look at monomial factors times e to the rx, where that exponent goes up to m minus 1. Right? This is straight out of chapter 4, section 4.2. Right? So I would like to show that those are solutions. Notice that all I'm doing here then is I'm just computing L of y. I'm just expanding out my asserted, my left-hand side. I'm just expanding that out in a different form. I'm capitalizing on the fact that algebra has allowed me to rewrite L in a very convenient way. And now I just got to compute this and show you get 0. And it turns out to be an easy calculation to see that this is equal to 0. First thing I'm going to do is I'm going to take the m factors that I have there and I'm going to separate them out in a certain way. I'd like to have k of them over here, and then 1 here, and then all the others there. Notice that this tells me that I didn't borrow too many. I didn't separate out more than I have, right? So that's perfectly legal. What does d minus r do? D minus r kills factors of x, right? That's what we showed up here. Hang on a second. D minus r kills a factor of x. I've got k d minus r here. I've got k factors of x. So each one of these d minus r's cancels with one of these factors of x. The k factors of x disappear after these k factors of d minus r. So all of those are gone. Now, of course, there's also the annoyance of there's these extra constants that stick out. That's going to create this k factorial here. it's going to turn out that we don't actually care about that, but let me just full confession. Of course, yeah, you do get that. And then lastly, d minus r, what does it do to a regular exponential? Well, direct calculation, that gives you 0, which means 0, and that means that L of y is 0, and therefore this proposed solution worked. Right? So we just proved that theorem. When you have a root with a multiplicity, multiplying by an extra factor of x, like we did there, up to one less than the multiplicity, always gives you solutions. Okay. All right. So we'll pick up here next time. See y'all later. Have a good Wednesday.